the NSA hid a backdoor inside the former encryption standard. Today we're gonna code a distributed cracking tool and try to recover the secret NSA master key. Let's get to it. Sup guys, welcome to today's show. So let's code an NSA cracker, shall we? This project I'm gonna do in JavaScript because I want it to run on every platform, so every one of you can chip in with your CPU power if you like. Alright, so first off, if you want to code along with me, you need to get Node.js. And you go to this site, nodejs.org, and you click get Node.js. Then you install it, and then I'm going to show you exactly how to do. But before we begin, let me show you on the blackboard what we are about to do today. Alright you guys, so the encryption standard is called elliptic curves, and I'm gonna explain it pretty simply because it's not very advanced on the top layer, so to speak. So it works like this. We have some huge number. This is just an example number, but it's about this length. And this is the public key. So this is published in the encryption standard, and everyone knows it. And this is called G for generator. That was a very ugly G, but yeah, this is called G. Alright, but we are interested in lowercase d. That is the private, the secret key. And this is the key that unlocks the entire thing. If you have this one, you can completely read everything if it's using this standard. And this is not the latest standard, but the numbers are the same in a lot of different applications. Alright, so how do you get this D? It's a very simple formula, actually. The formula is G times G is equal to something called T. So we know this G value and we know this T value, but we do not know the D value. And this is what we need to figure out. So if you are familiar with equations and stuff like that, then you must think, okay, but what if we just divide each side by G? Since we know both T and G, then we can just scratch these, and T divided by G is the secret key. And this is correct in principle. The only problem is we are talking about elliptic curves here. We are not talking about regular numbers. And there is no such thing as division. And I'm going to show you how it looks. So elliptic curves is a formula, and if you plot that formula on a graph using the real numbers, it's going to look something like this. So if we have the x-axis like this, and we have the y-axis like this, and you plot this formula, it's going to look something like this. So this is an elliptic curve. And if you take the numbers and you put it into the formula, you will get 1 point on this graph. So let's say this is a point, and this point is not on the curve because, as you can see, it's here. So this is not a valid number. However, this point is on the curve. And if you take all the possible values for x and y and you input it into the formula, you will get this one and this one and this one and this one and so on until you have filled this entire graph. And that's how it works. So each of these is, as you remember, the formula is d times g is equal to t. So one of these points is g and one of the points is t, and we know where it is. So what we need to do is we need to take this first g value, which is somewhere here, and we need to add it to itself. So if we say that this is g here, and we take g plus g, then we end up maybe here. And if we take this value and we add g to it, then maybe we will come here. So this is 3g and 4g and so on. So this is how we are going to crack this thing. Because the d value is how many of these hops we do when we plus g with itself. These are quite big numbers though, so it's not a very simple thing to do on your own. One needs to use a lot of computers running the same program. But you might ask, how can we distribute this between different computers if each and every one of them starts at the same location, g, and needs to times that with itself? So we plus g until we get to the right point. Doesn't that mean that everyone needs to perform the exact same work? Well, there is no division, as I said, and as I've shown you already, there is this plus. But there is one more possibility. We can plus other values than only g. So let's say instead of, when we're here at 3g, instead of adding another g, so we get here to 4g, we can plus 3g plus 3g. And then we end up many steps forward. So if we randomize this d value, or we get it from a server, then and let's say we have that in binary, so it's something like this, just for example. We skip the first one, and then we take the next one from left to right. If this is a 0, in that case we take g plus g. But next time it's a 1 here. So when we get to that point, we take the current point plus g, and then we add g to it. And then we do the same based on if this is a 1 or a 0. If it's a 0, we will do this. If it's a 1, we will do this. And that way we can, so instead of having, let's say, having to do n different combinations, we only have to do square root of n, which is a much smaller number. And this algorithm is called the double and add algorithm. And this is what we're going to use. So basically you don't have to understand all of this, but I hope you understand the basics anyway, that we have a method of trying out any value for d pretty efficiently. So if we have a server, let's say you connect to that server, you get some big number and a range. So let's say you're gonna do this all the way plus 65,000 or something, and you start working on that. And if you get a hit, you report back to the server, and we are done. If you don't get a hit, you still report back to the server and tell it, no, it wasn't one of them. And then you get a new number. And everyone who starts that program and runs it will get a new number each time you ask for it. And that way we can distribute this. And if we get enough people and we are a little bit lucky, we are going to crack the NSA master key, which is a very cool thing. So this is what we're doing today. We are coding this program and we are cracking the key. So we'll continue this right after this. Alright, welcome back you guys. Let's start this project. So I'm gonna go into my Linux machine, but you can use your Windows or Mac or whatever. Right, so I'm gonna create a new folder for the project and I'm gonna call it NSA Cracker. You can name it something else if you don't wanna use that one. I'm gonna set my home to my current directory. Alright, so when you have Node.js installed, you have the npm command. So we're going to use that to initialize our project. So we just do npm init -- yes. And then it's going to create this package.json file, which contains some information about the project. So the idea here is I'm going to code this. We're going to code the console version first. And then we're going to turn it into a web page, which will look something like this. Kind of cool, huh? So this is how it's going to look when you run it on the website. And this is the progress bar for the current block that we are currently working with, and we're gonna every number are very big numbers, so 256 bits, and that's why we're gonna represent it like this. So this is the IPv6 style with a couple of hexadecimal digits, and double colon just means that everything else is 0, and this is the number of bits that are fixed. But don't worry too much about that. It will become very obvious how we're going to do that. But we're going to start with coding the console version, which is this, but I'm going to write it in a way so we can easily adapt it to the website later. So this is the NSA Cracker, and the current version is 0. This project is going to crack the NSA master key. That's what we're gonna do. Ha! Pretty nifty, huh? Alright, so let's say our main file is main.js. We're gonna have a build script, because we're gonna base this on the TypeScript language, so we're gonna run tsc to build it. That's a TypeScript compiler. And then we're gonna have a start script, which is just going to run node against our main file. And what else? What else do we need here? And why is this red? Did I miss something? Weird. Okay, so build script, a start script, and that's just about it. I am Dr. Jonas Birch, and we can say this is MIT licensed. We're also going to need to add type module, so we can include several files in this project. And that's enough for now. Next, we're going to install the dependencies. So we're going to have one development dependency, which is the TypeScript and the stuff related to that. So let's start there. So npm install -save dev. So it's a development dependency. And we need TypeScript. And we also need the types for TypeScript. And we need the types for Node. So something like this. And when this is installed, just takes a couple seconds. And it looks a little bit weird on my screen. I'm not sure why, but it works. So now you can see it has updated our JSON file with this. So next we're gonna install the main dependencies, and both of these are my own code. So one is something which I call Fågelsjö/blocks, and that's the thing which is going to represent the numbers. And the second is called finite fields, and that contains all the math and all that stuff, so we don't have to worry about it. And I'm going to show you the page for one of these. So if you go to npmjs.com and we search for finite fields with an S on the end, then we get some information and some example code and stuff like that. So it's pretty easy to use. And we're going to use it so we don't have to worry too much about the maths. And we can also check for the other one, Fågelsjö/blocks. And it's pretty simple. So we have something of this type, and we can turn it into an integer and into a string, and we can turn it from an integer into this form, and so on and so forth. All right, so now we can start with the actual code. All right, so next we're going to initialize TypeScript, and we do that by running npx tsc --init. And this will create this tsconfig.json, but we will use most of the defaults there. So next you can open up the current directory inside of VS Code. I'm going to use the Sociopath SCP client because I need to connect to my remote server. But you just do it like you usually do. But I'm connecting to my server and I need to connect to my VPN. I always forget my VPN. Let's try this again. There we go. So I will go to my NSA cracker directory and open this up in editor, which is VS Code, as I have chosen there. Now we can just go into that folder and minimize. And this looks a little bit small. Let's see how it looks when we open a file. So let's create a file called main.ts. So this is going to be our main file. And I'm also going to create a make file so I can do this a little bit easier. If you don't have the make installed, you don't need this step, but I just do it for convenience. So let's say I have a build step which is going to run npm run build. I'm gonna have a run which is npm start. I'm gonna have a clean which just deletes all the JavaScript files, because the JavaScript files are generated from the TypeScript files. And I'm gonna mark as phony the run and clean steps because they do not build anything. And as default for all, I'm gonna use build. So something like this. And now I am able to run make, which will compile, let's see. What is it saying here? No inputs were found. Jeez. Oh wait, I forgot to save my my main.ts, didn't I? So it complained that I didn't have any TypeScript files. Alright, now I do. So I can run make, which will make this, and it will turn this TS file into a JS file. But if you don't have make installed, this is not necessary. You can just as much run just npm run build. And then you can run npm start to start the project, and I run make run. But it's just different commands for the same thing. I'm just used to you doing it this way. Alright, so now we have this empty project with everything set up. So let's go to this website again, npm.js, and we go into the finite fields with an S by the end. And we're going to copy some code from here. But first, let me just show you what the other package does. The one that I called blocks. So let's import. I want to import. Let's see where do I have these. I always forget where these are found on a Mac keyboard. Okay, so what do I want to import? I want to import make block from @fågelsjö/blocks like this. And let's say we have an integer which is of type bigint, and we set this integer equal to some huge number, and the n at the end indicates that it's a bigint and not just any regular number. And let's say that we have a block which is of type block, which we also need to import. So import type block from the same path, like so. And to turn this integer into a block, we just do block equal to make block, and we can provide an integer or we can provide a string. So it depends on what way we want to convert this. And then let's also say that we have some string, and we set this string equal to block dot to string, like so. And now we can simply console log this thing, and let's see what we get. So first we need to build, and then we can run. Okay, so this is what it turned out to be. So each of these fields separated by a colon contains 4 hexadecimal numbers. So it goes from 0000 to FFFF, which translates to 0 to 65535. And we have 16 of these fields. So this is actually 0, 0, 0, 0, etc. all the way up to these last 3 fields. And this 256, if you're not familiar with how IP numbers define blocks, you don't need to worry too much about this. Let's just say this will always be added, and it tells how big this block is. If it's just 1, the 256 means it's just one single number here, but it can also be a range, and that would make this number smaller. Alright, so this is basically all you need to know about this package. It's just for convenience, so we can represent big numbers in some nice kind of way. So next we need to use this other library, and I'm gonna copy some of this code, which I don't usually do, but it's easier that way since I have written it myself anyway. Plus it contains some characters like this Z here, which is not too easy to type without copying. So let's clean this up a little bit. And this is the field this is the curve that we are going to be working with when we go live. But for now, I'm going to use a curve called Birch 17, which we need to import. This needs to be something else in this case. And VS Code doesn't seem to help me very much. I think this is called, is it P? Let me just check real quick. So I'll go into the code, and where do I have that stuff? So let's see, it's inside of elliptic curves.ts. So let's see where, so here is the Birch curve, and it just tells that it contains 17 different numbers. Okay, I did have this. And some stuff like this, and some point on this curve, and other stuff, and a formula how to calculate with this curve. But we don't need to know the details in order to use this package. It's very easy to use, even if you know zero about elliptic curves or prime fields or whatever. So let's undo a little bit so we get this back, like so. And same, we're gonna use Birch bit length 17. Didn't I import this? thought I did. Oh, add declaration. No. We should import this from. Let me get rid of this stuff here. If I can remember how I do that. Let's see here. There we go. All right, so we want to import this Birch 17. From this one. All right. So we generate the prime field with these parameters, and we pass this Birch 17 curve. And now we can select a point on this curve. So let's say we have yeah, we can use this. So this we can remove. This is from before. All right, so let's say first we need a generator. So let's call this the point for the generator, and I also want to have a coordinate. So that's the two data types that we're going to use, and they are pretty similar. The coordinate can contain infinity as well. That's the only difference. And we convert back and forth by saying just and then pgen, for instance. We need to import this from. It's annoying that I can't use that automatic function for this, but we need just and we need empty and we need okay, empty we do have. So just pgen turns it into a coordinate from point to coordinate, and to turn it back we do fold of gen. And we can check if it's empty or not, so if it's infinity or if it contains a point. All this will be clear pretty soon. Alright, so let's see here. So we have this generator, and generator is a point on the curve. So let's set this to f dot p. So this is our starting point, so to say. And what we can do with this starting point, the generator, is we can double it, and we can add another point to it. So we can plus 2 points together. And also, this is the most interesting thing for our intents and purposes, we can search for this point, basically. So we give it a scalar, and it will, let's say it's 5. That means we're gonna add this point to itself 5 times. And this is how we're gonna crack, because we have the ending point, so we just need to figure out how many times we're gonna add that point in order to get the ending position. So let's say first that we try to, let's log this point first. I want to have a shortcut for logging. So let's create a log, which is a function from some arguments of type any array to void. And log is equal to console.log, like so. we can log this point gen. And then what else did we have? We had t and mt. So let's say we have t, which is a point. So we can say that our point is equal to, and then we use this c here, which is our curve. So c dot double, for instance, and we want to double our generator point, and then we can log the result. By the way, this should be mt is equal, because it returns a coordinate. Alright, so maybe everything will be a little bit clearer when we try to run this stuff. Begin, okay. Okay, so we need to generate that point first. So it's going to be equal to, and gen is a coordinate. So what we want to do is we want to first turn this point into a point like this. Point we need to import. And we'll also need okay, we have that. But we're not going to import this coordinate as a type. Let's just import it like this. And okay, so we turn it into a point, and then we turn it into a coordinate by calling just on it. And now I believe it's going to compile. No. Coordinate is a type and must be imported using type only. Okay, it's always a little bit tricky with this TypeScript stuff. Let's create our own line for types. So coordinate and point. So now let's see. It is complaining about that still. That's what I thought. We should not import it as a point. Why does it complain about that, by the way? It is a class. Both point and coordinate is a class, so we should be able to import this. Coordinate is a type and must be imported using a type-only import when verbatim module syntax. So let's go into our tsconfig and search for this, and let's set it to false. Oh, that's right. It's my fault, it's not TypeScript's fault. I always seem to forget this object-oriented stuff. So this is a new point, that's why. Okay, now it's going to work. Tuple begins. This is a point already. So what we just need to do is this. I have been coding so much lately that I seem to forget what I wrote just a few days ago. Type just big int is not assignable to type coordinate. So let's see. Just big int. Begins. Wait a second. This should probably be CP. Is that it? It's not attached to the field, it's attached to the curve. Right, so now we're on the right path. So this is what we should have done. Alright, now it's going to work. Yes. Okay, so we start out with this point. That's our basic point, our starting point. So the x-coordinate is 5 and the y is 1. And this is infinity, which is false in this case. So we take this point and we add it to ourselves. So basically what we do here is we have 5, 1 plus 5, 1 is equal to 6, 3. And this math might look a little bit weird, but this is how it works with this elliptic curve kind of stuff. So then we can try to double that thing again, or rather we can add so we take our generator and we add it to our current point. And then we do it again. All right, so and I didn't print the thing. So what we have here is 5.1 plus 5.1 plus 5.1 is this. And then if we add it to once again, we get this and so on. So this way we get a lot of different numbers by just adding our generator a bunch of times. So let's say we do this a couple of more times, like so, and let's just log the result here. So now we have added it a couple of times, and we end up with this 13.7. So let's say this is all we have. All we know is we have our starting point, our generator, which is 5.1, and we want to end up with 13.7. So we need to figure out how many times we need to add this to itself to get this. And this is how we're going to crack the key, because that is exactly what we are about to do. So let's call this our target point. So let's create a, let's see, our target, which is a point. And we also need to have a maybe target, which is the coordinate. And let's say that our target is equal to a new point, and we provide 13.7. And our maybe target is equal to just target. Like so. So how do we figure out how many times we need to add it to itself in order to get this? Well, we need to code the cracker. So let's say we have a function which is called the cracker, and it goes from our, let's see, we need our generator, but let's call it something else. Let's call it G for generator. And this is a coordinate, and we need a target, which is T in this case, which is also a coordinate, and we want to return nothing. And we can clean out this stuff. Let's say our cracker is equal, by the way, did we, right, it's void. So we have a generator of type coordinate, we have a target, we want to return void, and this is our function. Alright, so let's say we have a current point, which is a coordinate, and we need to have some counter. And let's say this is a big int, because currently we're only working with very small numbers, but we will be working with 256-bit numbers. So let's adapt everything to that from the start. Okay, so let's have a do loop. And we will set our current coordinate to the generator. That's our starting point. And let's set our counter to 0. We need to provide the n to specify it's a big int. So let's see. We can start by increasing that counter, because setting this to G is like multiplying it with itself, right? So that's our starting point. So let's see, check here if it's the point that we are looking for. So we need to have some equality function. So let's say if our equality function between our current point and our target point. If that is equal to true, in that case we are done. Maybe we can return the big int that we're looking for. So let's say we either have a big int or null if we didn't find it. So big int or null, or actually it's easier, we can return a regular 0 in this case since it's an integer type. So if we have found the correct point, we return the counter. Otherwise we move on to the next one. So let's see here, we need to do that equality test first. And then we set our current point equal to c.add, and we add our generator to our current point. And let's continue this as long as the counter less than 65535. And if we get down here, we can return a 0 indicating we failed. Okay, so how do we check for equality? So our equality function, it takes a coordinate A, a coordinate B, and it returns a boolean. So let's say we have these coordinates A, coordinate B, and we return boolean. So first we need to check if they are eternity or not, infinity. So if empty A, that means that A is infinity. In that case, we want to check if B is also empty. And in that case, we can return true. But if A is empty and B is not, we need to return false. However, if A is not empty, by the way, let's see, A is empty, B is empty. So what if B is empty? Guess we need to check that here. So if we get down here and B is empty, we also are false. However, otherwise we want to return, and we want to check two things. We want to, in that case, we need to turn this back into points. So let's say we have, let's call this MA for maybe A and maybe B. And and then we have the A, which is a point, and we have the B, which is a point. So we set A equal to fold MA, so we fold it into a regular point, and same here. And now we just want to check two things. Are the x coordinates equal, and are the y coordinates equal? So if a dot x is equal to b dot x and a dot y equal to b dot y. In that case we return true, otherwise false. Simple as that. Why is it complaining? E is equal to this boolean. Right. Sometimes these error messages are quite good. And what about this one? I'm not sure why this is complaining. Maybe it's some weird editor thing. So what do we want to do with this stuff? We want to run the cracker on our 2 points. So let's say we have a result of type boolean. No, this should be a big int. So our result is equal to our cracker, and we provide our gen, and we provide our M target. And then we can log the result. Alright? So let's see what it says. I'm pretty sure there's some error in here. While expected 70. While expected. So let's see here. We had some do somewhere, didn't we? Do, right. Okay, that's better. Number is not assignable to big int. That is also very true. So this should be 13n and this should be 7n. Alright, compiles. 7n is the result. So let's verify that. And we can do that. Let's see, we did have some extra coordinate. Yes, we have t and we have mt. So let's say mt is equal to curve.find, and I think I need to look at the manual here. Okay, so scalar generator. So we want to find 7n on our generator, and we can log empty. So if our cracker was right, that the secret key is 7, then we should get this result when we multiply. Which we didn't. Did we use the correct values? Let's see here. 7n in the generator, and we call the cracker with the generator and the target. Let's see how far off we were. What about 6? Okay, because I think we are probably off by 1. What about 8? Okay, there we are. So 13.7. So we reported one number too far, or whatever. So we start at 0, and we do the equality check against this. I think we should start it at 1. Because when we run 8 with the generator, we get the right point. So we want our cracker to reply 8, which it should do now. Yes. Okay, so we have a working cracker. Maybe we can also log every step so it becomes a little bit clearer. So before we do the equality check, we can do something like this. So we'll log, let's see here. Let's say that we log the generator to string. Is this equal to, so we take our counter times our generator equal to our current point to string, something like this. And if it is, we can log yes. So this way we see a little bit more what's going on. Okay, so we try to multiply it by 1 and we get itself. And we multiply it by 2, and by the way, this equal sign should only be one equal sign, because this is equal to this. And then we find the target point at this. So this is how it works. And maybe we can try to find some point which doesn't exist, because that will probably happen quite often. So let's say we have, I don't know, let's say we have 15, 7, I don't know if that's, or 15, 0 perhaps. It might be there. There are only 17 different points, I think, or 18 or 20, something like that, on this curve. Okay, so here we try quite a lot of them, and it's quite fast. So a block is going to be this many, 65, 5, 3, 5. And we return 0. We didn't get a yes. And if you look closely on these numbers here, you see that they are starting to repeat. So here we have infinity, and then we have numbers, and then we have infinity, and then we have the same numbers, and this is how every elliptic curve on a prime field works. The only difference is when we run it against the real curve, we have well, a 256-bit number field. So how many bits do we have here? We have something on the order of let's see here, well, 4 bits or 5, something like that. And we're going to run it against something with 256 bits. So it will be a lot tougher to find the right thing, but we are also going to make it distributed. So everyone who runs this program will get blocks assigned to them, and it will be cracked in a distributed kind of way. But now we have laid the groundwork. So all we need to do for this version is we need to shift the curve to the real one, the NIST P256 curve. And also we need to make it connect to the server. Because I have a server, we can run, we can use any HTTP client like curl or what's the other big one called? Postman. But I like the one which is called bash client that I wrote. So we can do get and then secret drbirch.com/ blocks, I think, or block. Let's try this. Yes, I can proceed. And this output is just because it's installing this bash client. If you have something else for this, you can use that. Okay, so it's not blocks. What about block? What was it? Let's see here. Block. Let me just check. API/block. That's right. then we will get assigned a block which looks like this. So the numbers are quite big, and it says that this is the NIST P256 curve, and then we will crack all the 65,000 possible numbers on this block, and then we will report back if we have found it or not. And we can also say stats, and we will get some statistics like how many nodes that's connected, how many blocks total that has been cracked, and so on. So we need to communicate with the server. So basically we'll just connect to it, grab this block, use it, and report back the result. All right? And that's what we're gonna do just after this. Did you know that I made a book about computer networking? You will learn how the internet works and how everything works under the hood. It's a complete beginner's course, but it has some advanced elements as well. And you will learn network design and network security and all different kinds of stuff. For more info, check out books.drbirch.com. That is books.drbirch.com. Thank you for your support. All right, you guys, welcome back. I'm gonna continue this project on my Windows machine, but you just carry on as before. So before we continue, I'm gonna show you a page from the NIST manual, the NIST specification of the dual EC standard. So here in the appendix, we find the information about the elliptic curve that we're going to use. So just to mention, this is the size of the field, and this is the number of points on the curve. And this is a coefficient that we use with this formula. This stuff you don't need to worry about too much. Here is the x and y coordinates of the generator point. So this is the point that we're going to plus with itself. And this is the target point. This is the public key of NSA. And we are going to find the private key, so the number of times we're going to add this to itself. And we don't need to copy anything because I already have this in the finite fields library here. So all we need to do is we change this Birch 17 curve to the P256 curve. So that's all we need to do in order to switch to the real thing. Like so. And the generator is the P point as before. This we need to change though. So let's copy this and put this in the same place here. So we don't need to do this, but this M target point we just set to the Q point. So now we have our generator, we have our target, and we have switched to the real curve. So we can test this out and see what happens. So let's compile this thing. And let's run it. And as you can see, it works the same, only the numbers are quite a bit bigger, and as you can see, it's not as fast anymore as before. So we need to take that into account. All right. We do need to change up a couple of things, because as currently we start at 1 and we count upwards towards this, and this should, by the way, be this. But we're not going to start from 1. We're going to start from, let's see here, not stats. It's going to be block. Because we're going to connect to this server, we're going to take this block right here, and this is what we're going to use as a starting point. And then we're going to, so basically the first one is going to be this, basically. And then 1 and 2 and 3, all the way up to FFFF. And then we take the next block. So that is how this is going to work. So for our cracker here, I'm gonna add a parameter. So let's call this, well, let's call it the S for start value. And this is going to be a big int. So the counter is going to be this S value. And we need to update the signature up here. So S is a big int. Okay. And what else? I think I'm gonna take this stuff right here and put it in its own function. Let's see here. I think I'm gonna do it like this. So let's create a function which is going to be called next. And we're not going to have any parameters to this. I don't think. No. And it's going to return a big int. So let's go here, and we take this next, which is a function from nothing to big int. And I'm gonna just take the inside of this the inside of this loop, put it right here. Actually, let's not return anything here. And we're gonna make use of some globals instead. So let's say we have something which is called current, which is a coordinate. And we also need to have the counter. So let count be a big int. And let's initialize this cur to the generator, same as before. And let's initialize the counter to 0 for now, just so we have some value there. So this we can remove. And inside of this function, we're not gonna set the counter to S. Yes, we are actually. Let's set this to S. And the current we have, let's see here. Yeah, we can set this to the generator again. And inside of this do loop, all we need to do is run the next over and over. And when this is done, we can run a done function. Same kind of signature. So inside of here, we run done. And since we have global variables, it will take care of the return value, so to speak. Don't need to return anything here. And this cracker doesn't either. Like so. And why am I doing it like this? It's because we are going to run these as asynchronous functions later on. So we can control a little bit how much CPU and so on we use. So instead of setting this result to the cracker, we are going to run this cracker on the first block. So let's say this is our, let's see here. This is our integer of our block. So to int we need to import. If we don't have it already, I don't think we do. So to int, and we need to create this block, which is of type block. We don't need to log the result like that. Don't need to do this. The cracker should not return anything. So at the top level here, all we are going to do this is going to be an endless loop, is we're going to run this cracker, and before we do, we're going to grab one of these blocks. So let's say we have a function called getBlock. So getBlock is a function from nothing to block. And we also need an identity. So an identity is something which looks similar to this, only smaller. And that is like how we identify ourselves against this server. So, and we're also going to have an email, and that is optional, by the way. So by default, we can set email equal to anonymous, and that is only because if you want to be a part of the competition, so if you become the one who cracks the real candidate key, then it might be useful to have a real email address, but anonymous is fine as well. And there's no way to turn the identity into an IP address or something like that. So everything will be totally anonymous. Okay, so let's see. We set this email to anonymous, and we also need the identity. And we need it in two different forms. So, or no, actually, we can have it as a string like this. Why is it complaining here? Oh, wrong thing. Okay, so how do we get an identity? Let's say we have function make identity from nothing to a string. So we're going to randomize this. So make ID is equal to nothing to string. So we need to have number, which is a big int. And we set this number equal to, and we call a function called util.rnd. Let's import util, which we couldn't do like this. So it's from the finite fields. Util has a lot of utility functions which are good to combine with this stuff. So util.rnd, and this takes two arguments. So how many bits are we going to use? So let's say 64 bits and 0 as a second argument. The second argument is if we want to put a highest number. So if we, for instance, say that the highest number is 100, the number will be between 0 and 99, so one less. Okay, so we take this number and we want to push it to the left. So we have 256 bits, and if we subtract 64 from that, what do we get? 192. And then we turn it into, let's see, maybe we can do it like this. Let's say we have a string. The string is equal to make block. Make block of num and to string. So let's try this function. So ID is going to be equal to make ID, like so. We need to do this down here. And then we can log this ID. And let's comment this out for now. So I just want to see that the make ID function works. Okay. Let's see if this compiles. To int, okay. From the wrong one. So to int is not from finite fields, it's from block. What else did we have? If equal, current, and t. T, what did we have here? It's this one, right? So this should be the generator, and cur we have, but we need to use our target here instead. What did we call it? M target. That's what we want to compare with. So our generator we have, so this target we don't need here. And actually we don't need this here either. We don't need this, nor this, nor this, or this. Block we need email and ID. And coordinates, counter. We need to change the signature here because we don't need to pass these coordinates since we have made them globals instead. And now I think we got most of it. Still red though, maybe because of this. Let's see here. And done function, we can just do something temporarily for now. So done is equal to a function from nothing to void. Just so we have something there. Alright, let's see what we got. Alright, so this is our identity in this case. Looks great. Okay, so that part is done. What else? We don't need to pass these. And we need to start up this process. So we can't just set cur to the generator. What we need to do is we need to find that point. So we run c.find and we provide the counter and the generator, like so. So that is our starting point. So now we need to code this get block. So how do we get one of these blocks? We need to connect to the server, right? So first let's get the URL. let's create a constant. Let's call it base URL. And this is this. And then we go here, and so let's see here. This needs to be an async function actually. So get block is an async. Maybe we don't specify that here. However, it's going to return a promise of a block, because all asynchronous functions, as you JavaScript coders know, they don't return the return type directly. It returns a promise to return type, which means that whenever this function terminates, this will turn into this. So if you don't know that already, you don't need to really know the specifics. However, you need to know that we need to define it like that. So getBlock is going to be an async function from nothing to a promise of a block. And how do we do this? First, we need a URL. And our URL is going to be our base URL plus, and the one that we're going to call is block. So now we're going to connect to this. So let's see, what is it going to return? Let's do it like this first. So we're going to await and this is global this dot what's it called? Not grab, but something similar. What is it? It was a while I coded this language. Fetch. Okay, so the first argument is the URL. So new URL based on this URL. And request in it. I think this is our parameters, our options. And what are we going to need for options? Well, the method is going to be get, because we're going to do an HTTP GET request. We also need some headers, which is an object, and this contains content type, application/JSON. And I think that's it, actually. And what does this return? A promise of a response. Okay, so let's create a response. Like this. And this operation can fail. So what we need to do is we need to check if we don't have a response or if the response is not okay. And what do we do in that case if we are not able to get the block? And this is the initial block. Well, I think the easiest way for now is we just return. We just return let's say a block or null. Let's not forget to change this right here. And then we can just return null, indicating that something went wrong. Otherwise, we're gonna get an object back, which is going to look something like this right here. So let's first create an interface for that. So let's say we have an interface for a response object, and it contains an error code, which is an integer, a number. It contains a curve, which is a string, and it contains a block, which is a string at this point. So let's say that we have an object which is a response object. We set this object equal to the response. We need to await this, the response.json. And let's do a sanity check. So if we don't have an object, or let's see, if the object dot error is not 0, or if the block is not inside of the object, or if obj.block is 0. And this question mark dot means that in case this object doesn't work, like if it's null or something, then this will return 0, the whole thing, instead of causing an error. And if this happens, we return null. Otherwise, we have this object, and the only thing we're interested in is the block, so we can return, we need to create the block. So we set the block equal to make block out of obj.block. And then we can return that block. Something like this. And let's, for the sake of completeness, put all this stuff inside of a try block in case something goes wrong. And if it goes wrong, we return null. Alright, so something like this. I think this might work just fine. So let's try it out. Let's keep this commented out for now. And let's not log the ID, but let's say the block is equal to get block. We need to await this get block. And then we just log this block dot to string. All right, let's see if this compiles. Block or null is not assignable to block. That is true. So I guess we need to set this block to block or null then. Block is possibly, that's true. So let's do this. It compiles. Let's see what happens. Look at this. We have successfully grabbed this block from the server. Pretty nifty, huh? Alright, so we know how to do this, but we also need to have a function for getting the next block. And isn't that just the same? No, it's not actually, because when we get the next block, we are going to report as well, not just get it, so to speak. So let's say this is report, and this too is a promise of a block or null, let's say. And we can copy quite a bit of this one. It will be not very dry, but let's not worry too much about that right now. So this is report. So it will basically be the same, but instead of the URL ending in block, we're gonna use report, and instead of get, we're gonna use post. Still having this header. But we need to provide object with our results. So let's create an interface for that. Since this is the response object, this is going to be the request object. So let's see if I remember this. We're going to have an ID, which is a string. We are going to have an email, which is a string. We're going to have the block, also a string. And we're going to have the candidate, which is a string. And this is optional. So the candidate is if we get a hit when we try to crack, this is where we supply it. Then I will get a list of all candidates and I can run some scripts to figure out if it's the correct one. So we need to create one of these request objects. So let's see here. This is going to be an object where the ID is the global ID that we have already. Same with the email. So let's see here. How do we know if we got a hit or not? We run the done function. So let's say the done function passes an argument right here with the candidate. And how are we going to define the type for this? Well, let's make our lives easy and make this a string. So we have the ID, the email, and the block is the current block, the one we are cracking. So let's see here. We need to store that somewhere as well. Well, we have it here, we can use that. But we need to make it in another format. So the block is going to be the block to string. And the candidate is our cand. Okay, so now we have the request object. Let's also have a request object, but in another form. So let's call this our string request object. And how do we get one of those? Well, we set it to json.stringify, and we provide our request object. So this makes it into a JSON string. And now we can just say that we have a body, which is this thing. And this we send to the server, and hopefully we get the same thing back as before. We need to update the signature. So report is now taking a candidate of type string. And do we have all of this? We have the block, we have candidate, which might be null. Let's try our report function. So first we get this block, and then so let's see. Let's just run it like this. So await report, and let's say we provide a 0 candidate, so we didn't find any candidates when we crack. That's what that means. And let's remove this for now. Let's go into this report thing, and before we return, we'll log the block we get back so we can see if it works. Block is possibly null. 149. Well, it will never be null, but let's do it like let's do it like this. So block to string or an empty string, something like this. Right, let's try this out and see if our report function works. Yeah, so this is what we get back. But I want to see the whole thing actually, not just the block. So let's log this obj instead. Let's also log what we send. Like so. Okay, so this is what we're sending to the server. We send the ID, we send anonymous as our email, block, we send this whole thing that we got from the server before, and an empty candidate. And what we get back is a new block that we want to crack. So everything seems to be working exactly as I was hoping it would. And let's say if we don't have a block, so we don't even have the initial block, in that case we need to fail. So console.error enable to connect to server. and then we do process exit 1. Okay, otherwise we have a block, and then we can start cracking. So we do not need to get another one. But we're going to run our cracker on this. Sorry about the sound in the background. It's my cat that is going a little bit crazy there. Alright, so let's see here. The cracker just does this. Alright. So we run our cracker, and then we get another block by reporting. And how do we know So the done function here, let's say we have a global thing. Which is a candidate of type big int. I don't want to shadow the variable name that we already have. Let's call this the global candidate. And when we start, we will set the global candidate to 0. And when we are done, we are going to set the global candidate to our current counter. Let's say we return true in this case. So if next, we break. So we need to give this next a return value instead. And let's say this is a boolean. So returning false means we didn't find the thing. We didn't find a candidate. So if next we break, and this means that we set this to 0, we run our cracker, and we report back this global candidate. We need to turn this into a string. let's say we have an scand, which is a string. So if we have one of these, we want to set our scand equal to make block out of this candidate, and we run to string. Otherwise, scand is empty. So something like this. And when we try this out, let's not run 65,000 per block. Let's just try like 5 or something temporarily. So that would be our next function, I think. No, our cracker. So let's say if this is less than 6, and we highlight this so we don't forget that this needs to change. Okay, let's see what we got. Block or null. Let's start with that one. Okay, so report. Okay, so if the report fails, what do we do if the report fails? Well, it's not much to do. Where did we define this block? We defined it as block or null. And report is block or null. This should be a wait report. Which means this shouldn't be null. At least not if we check it here. So let's do, for now at least, console.error, unable to connect to server, and this we will probably change. Maybe we could do console.warning. And maybe we can change this to while block is empty. So we do console.warning, and then we try again after some time. So global this dot set timeout, and we need a time handler, which is a function. And the only thing we're going to do is we're going to set block equal to await report as scanned. And this needs to be a promise of void then, I guess. And it needs to be an async function. So something like this. Can we do it like this? Because this will probably just loop. Tricky one. Let's not. We don't need to overcomplicate things right now. So let's make this a real error instead, and kill the whole thing for now. We can fix this in next version. Alright, and what else did it say? It complained that we didn't have types/node. I thought I installed that, but okay. npm install save dev at types/node. Let's see if it compiles. Oh, we forgot one, didn't we? We need to update our tsconfig, that's the problem. But let's fix this one first. So we run the cracker to int block. Well, this will never be null at this point. So all we need to do is full TypeScript. So let's just say if block, then this. And let's open our tsconfig and we go to types. We need to add node, like so. And now I believe it will compile. Almost. String literal will double quotes. Oh, that's right. JSON files need double quotes. Now it will compile. Alright, let's see what we have. Okay, we got a block which we are trying to crack. But did we only do one try here? So we call the cracker here, and we find this, set our counter to this. We are not increasing this. I guess that's a problem. So counter equal to S. Well, we do actually. Is it really this operation which took so long? Let's do some logging here. Okay, 1, 2. This goes pretty fast. And then we go to 1 and it freezes. So 1, 2. And we call next. So this happens, right? Then we do an equality check between the current position and target, which shouldn't return true, which means we increase the counter. And the current adds this. But why does it run the cracker twice like this? Because when we start the cracker, it should... right. We can't compare this to less than 6. Right. We actually need to have another counter, some local one. Let's call this counter prime or something, which is a big int. And this we are going to set to 1. And when this is this, then we exit. So let's try it like this. Okay, that's better. Now it actually seems to work. So as you can see, it's not only cracking 6 times or 5 times, but it's doing that and then grabbing another block and then taking that, and so on and so forth. So let's remove these. And let's not log it like this. So let's see here. Let's put some log message like something like this. And the block that we are cracking well, it's the make block of the other counter to string. Something like this. Actually, we have that in a global, don't we? So we can just say block here. Okay, let's try this again. Okay, we need to do like this at least. Oh, we need to increase this counter as well, of course. Why isn't it taking the next one? We need to have some better debug messages, I think. Maybe we can do something like we create a block out of this counter. Like so. This should make us see a little bit clearer. Right, so we crack this block and ending in 1 and 2 and 3 and 4 and 5. Then what? Then this cracker function terminates. Where do we run the cracker? Here. And if we have a G candidate, we do this, otherwise this. Block is equal to report. Okay. Did actually work, but why did it take so long here, and why did it fail to connect to the server here? Maybe we need to log when we connect to the server so we know a little bit better what's going on. Let's do it like this. Okay, so it's trying to report, but then not much is happening. Because it should make this report and return the block we get. And when we report this block. candidate. And the G candidate is 0 unless we run the done function, which will set this to the current counter. But the done never happens. So we run 5 next, and we return from the cracker. We try to report. Is it really the report that takes that long? Let's do like we did before. We log what we're sending. And what we receive. Alright, so now we should be able to see a little bit better. Okay, so we receive this. But then it freezes. Which means that this report happens, and if block is 0, which is not, so we go back to this loop, set the candidate to 0, and we should have a block at this point, which means that we run the cracker on the next. And what do we do there? Set the counter to S. Which is our new block. We reset the other counter, and the current is we are finding this before we set the counter. This is what we should do. It's weird that it become the result that we got. Could this really be the problem? Because now nothing happens. Okay. So we receive this, but why doesn't it? Where does it freeze? Because obviously we do get this, because here we log the receiving and here we log this green stuff. It's almost as if it gets stuck somewhere. But I don't seem to figure out where. Let's add some else messages. So what we report is the candidate. That's only if we have a G candidate. But what is slowing it down? Could it be this find operation which takes so long? I guess that's possible. Let's try it again. Okay, that seems to be quite slow. what is the S from the beginning? It's from this block right here. So that should be in order, but why does it take so incredibly long? It didn't before, did it? Maybe it was cached, and that's why. Yeah, that's probably it. But this is not actually a problem, because it's a problem now that we only take 5 attempts per block, but we are going to have 65,500 per block. So then this slowing down is not a problem, and it's nothing we can get around, because we need to find the block before we do anything else. So let's remove some of these log messages. Here we can still have it, so let's see. This is the make block of the counter at this point. To string or nothing. And this we still want. Maybe we can let it jump out a little bit. And this we can actually keep. And this we don't need. Nor this. Right, something like this. And now we're gonna remove this right here. So we crack the number of things that we actually should crack. And now I think everything will run fine. So first we find the elliptic curve point, and this does take a while and is supposed to take a while. But as soon as we have found it, it should be cracking quite fast. Because this is the really CPU intensive operation. But in my estimate calculations, this only needs to be done like once an hour or once. Oh, I forgot to change this. So this finding the EC point, this will only be done once an hour, or once every second hour. So this is not really a problem. If the other operation is fast and this is slow, that's no problem. If we do this once every 65,000 times. And we could possibly increase the block size to 24 bits instead of 16. That's also possible, but I don't think that's preferable, because cracking one block per hour, I think, is pretty well balanced if that is the case. We need to figure out how this works in practice as well. Alright, look at this. This is actually quite fast. It has almost done 100 just while we're sitting here. Okay, very nice. Yeah, this is our working version 1. So let's call this the NSA cracker v001. And let's update our package.json 001. And I think that will be all for today. Next episode, we are going to secretofthebirch.com miner. Then we're going to do this one. So we're going to take the JavaScript code that we have and we're going to apply it for the web, so we can have this nice, cool interface. And this also means that anyone who wants to run this cracker can just go to a link and run it. Yeah. So I really hope you liked this episode. It will be really nifty if we actually will be able to grab the correct key together. Please don't forget to like and subscribe so you don't miss the very interesting next episode. And thanks for watching. Thanks for today.